Hello everyone. This lecture of BP13 is about control flow. In particular, we're going to discuss functions. So far we've been getting familiar with the basics of programming. We've discussed memories, drive, or the structure of a computer. We discussed generalities about programming languages, and we are right now doing a practical introduction to programming. We learn about data, vectors, and so on. One thing we want to learn is what happens when you have specific needs, when you want to do operations which are beyond the available tools you already have. So for example, plus, minus, multiplication, and division, these are all tools that are available to you, but sometimes you want something specific. You may need a unique tool, something that does not exist yet, which is not available to you. Therefore, you have to work for it, create it, forge it, and then you will become able to use it. So this kind of tool, basically you can identify it when you're working. If you realize that you're repeating a lot of lines of code, copy pasting a lot of code, or you're reusing a lot of pieces of code you just wrote before, you probably need to write a function. So how does a function look like? The function starts with the keyword function and ends with the keyword end. For those who know about MATLAB, it's the same in Julia. It looks like this. Next to the function keyword, there is the name of the function. So here you give whatever name you want for your function. And in brackets here, round brackets, you will define the input arguments of your function. So that's how it looks. Of course, there are 3 dots here, and that's the place where you want to inject the instructions you want. So you want to put some code instead of those 3 lines. We'll consider 2 cases here. The first case will be a function that creates a new object. For example, an array, a float, or a string. So here we will consider a function that will create object A and that will return A to the outer scope of the function. So what does it mean? It means that when you will call this function, it will take one argument called B here, and it will create A equal B and return A to the main scope. So A will become accessible and modifiable in your workspace. So let's make an example. So you can take a clean REPL. So if you take a clean REPL and you type A, of course, A has not been defined before, so you should get an error, A is not defined. It doesn't exist. Let's define B. B, we will set it equal to a vector ones of 3. So B is simply a vector of 3 ones. The next step is to compile that function. So you can copy paste the code into the REPL and you press enter and you will get if you get a blue point, you should see a function that returns array. That's the name of the function. It's a generic function with one method. Now, Julia is aware about that function. So the function is now defined. Now we can use it. But we are here talking about a function that creates a new object. So the way to call that function is to make an assignment. So here we write A is equal to function that returns array, input argument B. So you should be aware that when you create a new object, you make an assignment. This will return the result of this computation into a variable A, now accessible in the scope from which you have been calling this function. Let's check it. Okay, type A in the REPL, and now you should see that A exists, and it's equal to a vector containing 3 ones. So A has been successfully assigned. So that's the example of a function that creates a new object and returns it. Another type of function is a function that modifies an existing object. So a function that modifies an existing object will have no return statement. Instead, it will take as argument several arguments, the object here that is being modified, and other optional arguments. As a convention in Julia, when your function modifies one of the input argument, there is a convention that there should be an exclamation mark between the name of the function and the tuple of input arguments here. So now we can write this, and the action that is made inside is to increment all entries of A by all entries of B without any return statement. So let's start with defining B. So for now we're starting from a clean REPL. So if you have an open REPL, you can close it by typing Ctrl D, and then you can reopen it. Then you're sure there will be nothing in the memory. So first step you want to do, you want to define B. So B equal 1 or 3 again. And next we're going to define A. So here I'm being lazy. I simply type A is equal copy of B. So copy B is a function that will allocate memory to hold A, and it will set all the values equal to the values of B. Next step, we can copy paste this function and type it into the REPL, press enter, and you get this function that modifies array. It's a generic function with one method. So now the function is defined and we can call it. So we call our function. There is no assignment here. There is no equal sign on this line. We directly call the function and we give the 2 arguments. So we call the function, and you can check what happens after calling the function. If you type A, enter, you will see the values of A. They are now set to 2, and the values of B, of course, they have not been modified. So this function, the call to that function, has been modifying the array A that was passed as an input argument. So talking about functions, of course, during the first lectures we have been using functions, and yes, you may have noticed some of them before. The first thing we did already in the first lecture, we have used the function println. This is what can be used to print information to standard output. So this function println takes one argument here, a string. When we were drawing a lot of circles and ellipses, we've been using cosine, sine, tangent. These are all functions, so that's the name of a function, cos. And here there's one argument, a floating point would be an angle. And in fact, even the basic operations, such as plus, minus, multiplication, division, and so on, if you reach the help of Julia, so you press question mark and plus, then you will see that even plus is actually a function. It can be called this way, plus and then a list of input argument. So plus is a function. One thing we learned about functions is that they can be vectorized or broadcasted. So a function can be vectorized. So for example, we take exponential. So if you take exponential of a, if a is a scalar, this will return a scalar. Now, let's consider that x is an array. Can I type exponential of x if x is an array? What will this return? You can give it a try, but if you type an array, you will get an error. No method matching exponential of a vector. This is because what we want to do here is to broadcast exponential to all entries of an array. So what we would like to do is to provide an array and take the exponential of each of the entries of this array. And so you should remember, when you want to do this type of operation, when you want to do an element-wise exponentiation of the entries of the vector, you need to put a dot here to state that this is a broadcasted operation. So this will work. If you have a dot here, it will work, and it will return an array with each entry being exponents of the initial vector. So let's quickly have a look at an example which I will put in the folder for the lecture. So that's the exercise we were solving together during the two last lecture. We constructed the geological map. You can see that I pimped it a little bit, so I've removed the double entries such that these all look nice. And I've also plotted on top of the map, I've plotted the dots with the colors corresponding to the measurements or identification of rocks made on the field. So it all looked good. But when we did this exercise, there were lots of code cells. We were repeating a lot of code. We were basically copy-pasting a lot of things. And for example, we can check how these lines and how the color pixel map were defined. So if you look in the initial code, the contact lines, the black lines, were all plotted by using this pattern, xc times tangent something plus another thing. This pattern is repeated everywhere. And when we plot the geology, of course, when we are plotting the geology or the pixel map, the colors corresponding to the lithology, we were using a similar information because these domains are delimited by the lines. So what is the common ground here? The common ground is naturally the equation of a line. Y is equal ax plus b. So if we take one example here, we have the coordinate x. We have a, tangent of an angle in degrees, tan d, plus b. That's the pattern. So out of these 6 lines of code, we can identify actually the usage of 6 equations of a line. So when you identify this kind of pattern in your work, it means that it is probably time to think about writing a function. So what about typing a function that will compute the equation of a line? So let's do it. We can generate a code cell. And this function takes as input x, the angle alpha in degrees, and b. That's how it is typed. So function, line equation, x alpha b. Inside a is defined as the tangent of alpha, assuming that alpha is given in degrees. So tangent d takes alpha in degrees. And this function is a function that returns an object. This object is y is equal a times x plus b. End. 4 lines. If everything goes fine, then you should get a green tick mark, and this line equation is now a generic function with run method. The advantage here is that the equation of the line is typed only once. It's typed here. Y is equal ax plus b. It's typed once in this function. And prior to this, we were hard coding the equation of the line 6 times. Now we can simply use our function, and we're sure that we will not make any mistake in the equation of a line. Of course, here it's a bit of an overkill because the equation of a line is a very simple expression, but sometimes you have to deal with very complex expressions. And using a function will really simplify your life. So here you see how to make the color map. You can use line equation. XC2 are the 2D coordinates, the 2D coordinate x of each of the pixels. So here we want to broadcast the function to all of these pixels. So we use the dot here. To draw the lines, we are using vectors. So xc is a vector, xc_lim and xc are both vectors. So we also want to broadcast line equation to this vector. So we use a dot notation here. And you can give it a try. You can check the file which is uploaded on OLAT, and you will see that you get exactly the same result. So that's one way, one example of usage of a function applied to the exercise we did together. The advantage here is that since the equation is typed only once, there is much less risk of making a bug or a copy-paste mistake. So that's it for functions. And more or less that's it for the part of the lecture about control flow. So we've learned about control flow. We've seen how to use for, while loops. We've learned about conditional statements like if or while. And we've learned how to combine these things together. You also learn about functions now, and we've even been combining these skills to make basic or not so basic figures. So we're on the right path, reaching half of the lecture. Thanks for your attention.